We have 2 sections left in chapter 11, and we're going to finish those up today and tomorrow, and then wrap up the end of the year this week. So let's get going with section 11.8, which is spheres. And we're going to go through just some quick notes here. A sphere is defined as the set of all points in space equidistant from a given point. Remember, a circle is the set of all points in a plane that are the same distance from a given point. So a sphere is in space, it's three-dimensional. With a sphere, it has a center, here C. That's the point that the points on the surface of the sphere are equidistant from. We have the radius, which is a segment going from the center to any point on the surface, and also the length of that segment. We can have a chord of a sphere. We can have a diameter, which is the chord that goes through the center. We can have tangents to a sphere, and so on. So, as with circles, the terms radius and diameter also represent the distances of those lengths, and the diameter is always twice the radius. I'm going to give you the formulas for volume and surface area of a sphere, and then I'm going to show you some explanations of why these work. Volume of a sphere is 4/3 pi r cubed. Volume is a three-dimensional measurement, so we cube the radius. Surface area of a sphere is 4 pi r squared. The formulas are similar. One has 4/3, the other has 4. I always remember that the 4/3 goes with the r cubed. Volume is three-dimensional. Area is two-dimensional. Here's some justification for why this works. Push this. That. There we go. So if we watch this video, what we see is a cone going down into a hemisphere. And if you look at it, the height of the cone is the same as the radius of the hemisphere, and the radius of the cone is the same as the radius of the hemisphere. And when the cone pushes into the hemisphere, it makes a cylinder. The cylinder has a height that's equal to the radius of the hemisphere, and the cylinder has a radius that is the same as the radius of the hemisphere and the radius of the cone. So if we put this together, we have that the cone plus the hemisphere, so plus half of the sphere, adds up to a cylinder. And we know the formula for a cone, 1/3 pi r squared h. We're going to try and find the formula for volume of the sphere. And we know the formula for volume of a cylinder, pi r squared h. Now, in that picture, in the video, the radius was the same as the height. So this is 1/3 pi r squared times r. R squared times r is r cubed, plus half the sphere equals pi, and again, it's r squared times r. R squared times r is r cubed. What I'm going to do here is subtract this 1/3 pi r cubed over to the other side. So half of the volume of the sphere is pi r cubed minus 1/3 pi r cubed. That's 1 pi r cubed minus 1/3 pi r cubed. 1 minus 1/3 is 2/3 pi r cubed. Now I want to get rid of this 1/2, so I'm going to multiply each side of the equation by 2. On this side, the 2 cancels. Over here, 2 times 2, the volume of the sphere is 2 times 2 is 4/3 pi r cubed. There's the formula that we saw on the previous page. For the area formula, I'm just getting the work is all in this link. What we're going to do is we're going to take a sphere and dissect it into a whole bunch, n, pyramids of heights that are equal to the radius. So if you look as I drag this red dot, this is pulling out one set of them. We see that we get a bunch of pyramids where the height of each pyramid is the radius of the circle. So then we can think about some calculations here. A1, A2, and so on. There's n pyramids. The area of each base we're calling capital A. The total, we're going to talk about the total volumes of the pyramid and the total volume of the sphere. So the total volume of the pyramid is the volume of each pyramid, which is 1/3 its base area times the height of the pyramid, which is the radius of the sphere. So we'd have to add up all of these volumes of the pyramids to get approximately the volume of the sphere. Now, it's not exactly a sphere because each of these has a flat base and a sphere would be totally rounded. We can factor the 1/3 and the r out of these areas. So I have 1/3 times the sum of all the base areas times the radius of the circle, or the sphere, is about 4/3 pi r cubed. Now, as n goes toward infinity, as we break this up into more and more of these little pyramids, that area of all the pyramids gets closer and closer to the surface area of the sphere. And what we're trying to do here is come up with a formula for surface area of a sphere. So I'm going to multiply that 3 over and divide by r, and what we get is the surface area of the sphere is equal to 4 pi r squared. This one's a little more complicated, and it uses some ideas of calculus where you break something into smaller and smaller pieces and see what happens as there are more and more of those small pieces. I'll put this link up with the notes today in case you want to take a further look at it. So just to do some problems, here we're given the area of a sphere is 12 pi. We want to find the volume. Well, area is 4 pi r squared. We want to find the volume, which is 4/3 pi r cubed. So we need to find the radius. Divide both sides by 4 pi. Here I get r squared is 3. Take the square root of both sides, and radius has to be positive, so the radius is square root of 3. So I'm going to take that radius and plug it in. 4/3 pi times the square root of 3 cubed. Now, just think about this. When you have square root of 3 cubed, that's square root of 3 times square root of 3 times square root of 3. When I multiply 2 of those, I get 3, but I still have this third square root of 3. So when I multiply this together, I get 4/3 pi times 3 square root of 3. The 3 in the denominator and the 3 here cancel out, and my final answer is 4 pi square root of 3. That's an exact answer. Leave it in that form. Here I have a plane that passes 4 centimeters from the center of a sphere with a radius of 11 centimeters. I want to find the area of the circle of intersection. So I have a sphere, and the plane, this is like a geometric plane, is passing 4 centimeters from the center. So it's cutting through up here where this distance here is 4 centimeters. We've done problems like this back in the circle chapter. I want to find and the radius of the sphere is 11 centimeters. So the radius of the sphere goes from the center to any point on the surface. The point that's helpful is if I connect it to the edge of this circle. That's 11. I want to find the area of this circle, which means I need the radius of that circle. So what I have is a right triangle where one leg is 4, the hypotenuse is 11, and the other leg is r. So I'm going to subtract 16 from both sides. So I have 11 squared, which is 121, minus 4 squared, minus 16, and I get 105. Now I want to find the area of the circle. So to find the area of the circle, I'm going to use pi r squared. So I might as well just take the r squared, the 105. Pi times 105 is 105 pi centimeters squared. I don't need to take the square root of 105 and then square it in the formula. I might as well just plug the radius squared in. One more problem. We're going to find the surface area of the solid generated by spinning this figure around the y-axis. And typically we would have done a whole activity with these volumes of revolution, but that's something that we had to skip this year. So what we're talking about here is taking this figure, which is a quarter of a circle on top of a triangle, and spinning it around the y-axis. And when we do that, each point here I can reflect over. And what we end up with, if you spin this, is a hemisphere on top of a cone. And I'm not going to draw this very well here. The cone, the triangle, when you spin it, becomes a cone. This quarter of the circle, when I spin it, becomes a hemisphere. I want to find surface area. So I have up here half of a sphere, a hemisphere. Formula for surface area of a sphere is 4 pi r squared. So I'm going to take half of 4 pi and the radius squared. So I need the radius of this hemisphere. It goes from the y-axis over to the point 32. So the radius is 3. Then I need to look at what other surfaces I have. I have this lateral area of the cone going all the way down. Remember, the formula for lateral area of the cone is pi RL. So pi, I need the radius of the cone. It goes from the center out to 6, 2. So the radius is 6. And I need the slant height, which is here. So if this goes over 6, and then it goes from a height, this y-coordinate is 2, down to -6, that would be 8. So the hypotenuse of this right triangle would be 10. So that's pi RL for that outside part of the cone. And then I have this ring between where the cone and the hemisphere are. So that is a big circle with a radius of 6 minus the circle on the inside with a radius of 3. So here I can simplify a little bit. Half of 4 is 2 pi times 3 squared. 2 times 9 is 18 pi. 6 times 10 is 60 pi. 6 squared is 36 pi. And I'm going to subtract 9 pi. And when I combine all of these, because they are like terms, I have 18 plus 60 plus 36, take away 9. I get a total of 105 pi. There's no units here. That's my final answer. So you're going to do some problems with spheres today. We're going to keep it pretty simple. Well, then we're going to talk about ratios of area and volume in section 11.9 the next 2 days. And there will be a very short graded assignment on Thursday that will be your last grade of the school year.